Whoops. No, I think that's okay. Yep. And we are going to look at section 3.4, exponential and logarithmic equations. And you've seen these before. I may do these in a slightly different way than how you dealt with them before. You'll have to tell me as we get into things if this is the way you saw them last year. And I kind of need this particular method because what you saw last year won't work for certain types of equations as we get into harder things tomorrow. And the method I'm going to show you today will always work for these, so we'll see where we are. But this is section 3.4, exponential and logarithmic equations. And to solve these things, there are really only two different tools we're going to use. The first thing we're going to deal with is the fact that exponential functions and log functions are inverses of each other. I'm just going to call that first tool inverse properties. So the fact that these things are inverses, one will undo the other. More with that in a moment. The other, have you heard the phrase 1 to 1 before? Did you talk about that when you talked about like inverses earlier in the year? Okay, so I'm just going to write that down and I'll define that in a moment. We need to use what we call our 1 to 1 properties. And that's enough. Please, yes. If anyone needs to move seats so you're a little bit closer, please do. So the first thing we have to deal with are these inverse properties. Our definition of two functions being inverses is, well, the informal definition is they undo each other like a square and a square root. But the formal definition is if you put one inside the other, they cancel each other out and just leave you with an x. Our definition of functions being inverses, we can say f of x and g of x are inverses if f of g of x equals x and g of f of x equals x. You've definitely seen this one before, both in Algebra 2 and earlier, I believe, this year in pre-calc when you dealt with your function unit. Does this look a little bit familiar? You'd plug one into the other, see if you just get x when you go through some algebra to simplify things. Same with the other way around. With this in mind, we defined log base a to be the inverse of a raised to the x, which means if you put a log base a, well, first of all, let's start with this one. If we want to do log base a of a raised to the x, putting an a to the x inside of a log base a function, the log base a, the a raised to the, those things cancel each other out, and you're just going to get x. Hello, welcome. And hopefully we'll get a couple more people. Going in the other direction, if I do a raised to the log base a of x, again, I'm putting a log inside of an exponential function. They cancel each other out, and they just give us x over there. And this is one of the ideas we'll need to use to solve some equations. And we really just sort of started. I am still recording things so you can get the beginning of the notes a little bit later if you want. But our first tool for solving equations that we're going to use are our inverse properties. You put an exponential function inside a log function, they cancel, just giving you the x. If you put a log function inside an exponential function, again, those ideas cancel each other out, just giving you x. Before we get into some equations, though, I just want to do some simplifying. Let's simplify. First of all, let's do log base 3 of 3 raised to the 2x minus 1. Well, according to my first property, if you do the log of an exponential raised to something, I think our answer is just going to be whatever was in the power up there. This is just going to end up equaling 2x minus 1. That seem reasonable? Can you very quickly simplify the natural log of e raised to the x squared? Again, using our inverse property. Answer is, don't think too hard, x squared, the thing that was in the power. And if I have 2 raised to the log base 2 of 4x, well, according to our other inverse property, what's that going to become? Say louder. 4x. The 2 and the log base 2, they cancel each other out, just like we have over there. And we're going to get 4x out of that. Last one. E raised to the 5 ln x. Does anybody have a problem? Maybe my question should have been, what is your problem here? Yeah, I'm not okay with that. Going back to my inverse property thing. I need an e and just a natural log. You can't have the 5 there. Hello. Any ideas how I could kind of get rid of that 5? Why don't we do that? Doesn't a number before a natural log or any sort of log really mean e raised to the natural log of x to the 5th? Those of you just getting here, we kind of just started, but I'm recording stuff, and I'll get this up on Google Classroom a little bit later so you can get the beginning of our notes from today. Now, though, that I've done...
I'm leaving early.
Oh, you're leaving.
Yeah, in 30 minutes.
Okay. This is going to end up giving us x to the 5th over there. Does that idea make sense? These are our inverse properties. And the quick version is, if two things are inverses, they undo each other, just sort of giving you x over there. F of g of x equals x, g of f of x equals x. If I plug an exponential function into a log, I just get the thing that was in the power. If I plug a log into an exponential function, I get the thing that was inside there. We're going to use this idea in a moment to solve some equations. The other ideas we need to use are what we call our one-to-one properties. And we can say that a function f of x is one-to-one if each y value has only one x value. A function is one-to-one if any given y value has only one x value. So for example, f of x equals x cubed is one-to-one. If you know your y value is 8, what cubed gives you 8? 2. If your y value is 7, what cubed gives you 7? Cube root of 7. G of x equals x squared is not one-to-one. If y equals 4, what's x? Oh, that's a problem, because I said each y value can have only one x value, and that y value has two x values. That's why we would say x squared is not one-to-one. X cubed is one-to-one. The reason we're talking about this is because both exponential functions and logarithmic functions are one-to-one. Exponential and logarithmic functions are 1, 2, 1. If you know the y value, there is only one x value that's going to work for that y value. This is sort of the opposite of just our function definition. Every x has only one y. Here, every y has only one x. Okay, so this is sort of it for the theory behind this stuff. Let me show you some equations, actually. Okay, that's great. Kirti, are you still going? Or are you okay? You're okay. Okay, so solving some easy equations. Yep. Where are we? Are we? I think I'm on the screen. Tomorrow will be all about solving harder equations. We have 4 properties that we're going to use. First property, exponential functions are 1 to 1, which means a raised to the x equals a raised to the y. If we have an equation like that, I know for a fact that x has to equal y. Similarly, since logarithmic functions are 1 to 1, if I have log base a of x equals log base a of y, I know for a fact that over there, x equals y as well. These are supposed to be double arrows. Third idea we'll need to use, our inverse property with logarithms. Log base a of a raised to the x just equals x. And our fourth idea, inverse property of exponential functions, log base a of a raised to the log base a of x. Oops. Equals x. These are the 4 tools we're going to use to solve our equations. Really, it's just because by definition of the log base a and a raised to the x being inverses. By definition, since they're inverses, if you plug one into the other and the other into the first, they cancel each other out, just giving you the stuff that was inside. That's exactly what's happening here. I'm plugging log base a, the inverse of a raised to the something, inside my a raised to something. By definition of them being inverses, they cancel each other, giving you x. Don't think about it as, well, I know the a, this cancel. Think about it as they're inverses, so they undo each other. Okay, some easy equations. Let's look at 3 raised to the 2x minus 1 equals 3 raised to the 4x plus 5. By my 1 to 1 property for exponential functions, I know that since my bases are the same, the exponents have to be the same. I know for a fact that 2x minus 1 has to equal 4x plus 5. That's really easy. Go solve that equation. -3, I think. That's how we can use our 1 to 1 property for exponential functions. Obviously, they'll get a little bit more involved, but this is the basic idea. Using our 1 to 1 property for logarithms, let's look at the equation natural log of 2x plus 1 equals the natural log of 3. Guess I probably should have said in the first one that's true by our first 1 to 1 property. Here, by our logarithmic 1 to 1 property, I know that the stuff inside our natural logs has to be equal. So go quickly solve that one. X should equal 1. Natural log of 2 times 1 plus 1, natural log of 3 equals natural log of 3. Sure. There is one thing we do have to be a little bit careful with when solving equations that have logs in them. Sometimes, what do you call those answers that sometimes you could get that aren't actually answers? Extraneous. We could get extraneous solutions. Note with these things. We could get extraneous solutions. My check for an equation with logs in it is I just have to make sure that whatever number I get wouldn't give me a negative number inside a logarithm. So why don't we just say we cannot have a negative inside a log. I don't need to see any plugging in check or anything. You're just going to take a look at your answer, x equals 1. If I plug in 1, is the stuff inside this log positive? Yeah. Clearly this log is positive. I'm good. I've got my answer. I would like you to quickly solve natural log of x equals natural log 2x plus 9. And I'm thinking x equals negative 9. Good? Good? Why are you shaking your head? If you try to plug this in, 2 times negative 9 plus 9, that's a negative number. Plus, if you plug it in over here, that's a negative number. We got one answer, not because we did anything wrong, but because of sort of the nature of logarithms, we found an answer really outside our domains here. What we're going to say for our answer is there is no solution. But I do want to note that I considered negative 9, and it wasn't good, so I'm ruling it out. I'm going to say x equals negative 9 is extraneous. That's what we're going to say here. And again, my check is that negative 9 gives you negatives actually inside both of those logs. Might not always be the case, might be only inside one log and the other one is okay, but if it makes any log negative inside, not okay. The more interesting stuff. Let's look at 3, am I on the screen? Yes. 3 raised to the 2x minus 1 equals 15. To solve this one, I'm going to make use of my inverse properties. And here's where this might look a little bit different than how you dealt with this last year, but I kind of need this inverse idea for some of the equations coming tomorrow. So stick with me on this. I don't have 3 raised to something on this side, so I can't just like set the powers equal like I did in that first example I gave you. I need to get rid of this 3 raised to the something. And I can do this by taking the log base 3 of both sides. I am going to go and take the log base 3 of both sides. That is going to give me log base 3 of 3 to the 2x minus 1 equals log base 3 of 15. Now, by my inverse property, what does the left side become? 2x minus 1. The whole point of our inverse property, and the whole reason I'm taking the log base 3 of both sides is because I want to cancel out that 3. I'm going to get 2x minus 1 equals log base 3 of 15. And this is all by my third property that I gave you, the inverse property of logs. Logs undo exponential functions. Well, I don't know what log base 3 of 15 is off the top of my head. We'll use the calculator in a little bit. But I first want to get an exact answer for this thing. Well, that shouldn't be too bad. I can add 1 to both sides and say 2x equals 1 plus log base 3 of 15. Divide both sides by 2, and we're going to get x equals 1/2 times 1 plus log base 3 of 15. And that's my exact answer for this. Before I go on, this isn't how you saw it last year, right? You saw it just sort of move things around. Did you see it like this last year? No. Do you follow what I'm doing? We'll do a few more like this. Go to your calculator now. Let's get a decimal for this. In the homework, every problem is going to say give an exact answer. I'm done. And give a decimal rounded to 3 places. Remember to do this one, you're going to have to go use your change of base formula. But I feel like we can probably type this whole thing in one step. Let's see. I'm going to do 1/2 times in parentheses 1 plus natural log 15 divided by natural log 3. About 1.732, which is about 1.732. This is the better answer because it's exact, but this probably means a little bit more, and this one's probably the easier one to go plug in if you want to check that thing. If you do 3 raised to the 3 raised to the 2 times 1.732 minus 1, you're pretty close to 15, and I'd be closer if I just gave more decimals there. Okay, let's do another exponential equation where we have to use its inverse to get rid of things. 5e to the 3x equals 17. You're actually not ready to use any inverse properties here. You got something else to get rid of. So do what first? Oh, you know what to do first. Well, the 5... Let's divide both sides by 5. I don't have a natural log here or anything like that. I've got a multiplication problem, and I can get rid of my 5 by dividing both sides by 5. So I'm going to say e to the 3x equals 17/5. I now want to get rid of my e by doing the inverse of that. What's the inverse of e raised to something? Louder? Natural log. I'm going to go and take the natural log of both sides. I'm going to get the natural log of e to the 3x equals the natural log of 7/5. This is really just like me multiplying both sides of an equation by 2, or squaring both sides, or taking the square root of both sides. Here I'm just taking the natural log of both sides. What does the left become? By our inverse property, what's the left? 3x. You're going to get 3x equals the natural log of 17/5. Divide both sides by 3, or multiply both sides by a third, and I'm going to say 1/3 natural log of 17/5. That's the exact answer. Go to the calculator, we'll get a decimal, and I don't even think we need the change base formula here. You've got a natural log button, just use that. Connor, what do you have?
408.
That sounds good. If this was on the calculator part of the test, I'd probably go and check it just to make sure things are good. But yeah, things will work if you plug that in. Are you starting to see my inverse step? Because again, we're going to need that for what's happening tomorrow. I've got 2 more examples to show you. Let's look at log base 4 of 5x plus 1 equals 3. The inverse of a log base 4 is an exponential function, a 4 raised to the something. So what I'm going to do is do 4 raised to both sides. I'm going to get 4 raised to the log base 4 of 5x plus 1 equals 4 raised to the third. By my other inverse property, what does the left become? That's the point. The 4 and the log base 4, they cancel each other out because they're inverses. That's how we defined them. I'm going to get 5x plus 1 equals, well, 4 to the third, that's not bad. 64. Take a moment, finish it. X here should be 63 over 5. One more. Natural log of 4x minus 3 equals 2. What would undo a natural log? E raised to both sides. E to the x is the inverse of natural log of x. So I'm going to go do e raised to both sides. E to the natural log of 4x minus 3 equals e to the second. You go finish this thing. And let's do both an exact answer and a decimal answer. I think the exact one should be e squared plus 3 over 4. Shrithika, do you have a decimal for this? Good. Make sure, of course, you're being careful with parentheses when you plug in and things like that. I think the big new thing today was the idea of those inverse properties to undo things. Again, we're going to need those for stuff to work out tomorrow. But we'll save the harder equations for tomorrow. Okay, I'm going to stop this.